Thank you once again.
With this, we conclude the inaugural function. Stay tuned for the first invited talk of the event by Professor K.T. Selvan from SSN College of Engineering, Chennai on teaching and learning electromagnetics in 2020, chaired by Dr. P. Mohanan, CUSAT, starting next. Thank you.
Very good morning. Can you hear? Hello?
Yes, sir. Yes, sir.
Very good morning. With great pleasure, I extend a cheerful welcome to all participants of APSYM, a great event in India started by my guru, Professor K.G. Nair. I find immense pleasure in introducing our invited speaker and my friend, Professor Krishnaswamy T. Selvan. We are really thankful to him for taking the time out of his busy schedule to deliver this talk. Dr. Selvan has been a professor in the Department of Electronics and Communication Engineering, SSN College of Engineering, since June 2012. From early 2005 to 2012, he has worked at the University of Nottingham, Malaysia campus. He also held different positions in India and abroad. I am not elaborating all these things. Mr. Selvan's teaching and research interests include electromagnetics, antenna theory, design, and measurements. In these areas, he has authored and co-authored a number of journal and conference papers. He is an editor of the format and earlier one of the editorial board of International Journal of RF and Microwave Computer-Aided Engineering and International Journal of Antennas and Propagation. He is a trust chapter of IEEE Antennas and Propagation. APS Regent and Distinguished Speaker Program for promoting EM education. He was also a distinguished speaker for 2015 to 16 under this program. Dr. Selvan is a senior member of IEEE and a fellow of Advanced HE. Now I invite Professor Selvan to deliver his talk in teaching and learning electromagnetics in 2020. I welcome Professor Selvan.
Yeah, thank you very much, Professor Anandan. So thank you for the invitation. So I will share the screen now, and I assume that I have half an hour because the next session has to start at 11. Am I right?
No, sir. We have put a there is a gap. Next session is at 11:30. So you can
11:30. Okay. And thank you. So I will just share my screen now.
Thank you.
Okay.
So is the screen visible?
Yeah.
Yeah. Okay. So good morning, everyone. So I would like to thank Professor Anandan for this invitation to talk at APSYM 2020. So the talk is on teaching and learning electromagnetics, a topic close to most of our hearts. So the broad objectives for this talk would be the challenges that teaching and learning electromagnetics especially faces, and then to suggest some approaches and recommendations. These approaches and recommendations that we'll be discussing are not very prescriptive, rather generic philosophy kind of suggestions for considering this. And then to share some specific ideas on how we can, personal ideas on how we can teach some of the electromagnetic concepts. So here I'll be taking an assorted topics, a list of topics, and then briefly discuss how this can possibly be taught. But of course, all these are, the ideas of the speaker. So please feel free to reject, accept, or as you consider them appropriate. And then some reflections on nourishing and promoting electromagnetic education. So these are the broad objectives for this talk. So electromagnetics is very important. That is something which we have been telling all along. So it is a perfect example of how a subject has to be. this may be a biased statement from those of us in electromagnetics, but the coherence, the symmetry of the field equations and the conceptual richness of electromagnetics, I'm not sure how many other subjects can parallel that. And the way it beautifully connects mathematics and physics, and especially when we look at the model building that was very instrumental in, for example, Maxwell coming up with his displacement current or other equations, or Faraday's lines of force. That's a very beautiful connection between mathematics and physics. And of course, wide range of applications ranging from digital systems, bioengineering. I will have something to say on this as we go along. So electromagnetics is obviously very, very important. So what are the challenges? So when we consider the challenges facing electromagnetic education, I think there are two broad perspectives from which this can be considered. One is the educational trends and technological advances. The last couple of decades have seen an explosion of technology. So if you just look at this Wikipedia site, a list of emerging technologies in electronics, and of course this site also lists in agriculture, in optoelectronics and all. It's amazing. I mean, extensive list of areas have been emerging. So which means it obviously puts some pressure, as we will just mention. And in this, in the emerging technological scenario or landscape, there may be a tendency to see electromagnetic courses as old-fashioned or outdated. That is one challenge we probably face. And it could often be seen as an easy target for trimming, right? Because the curriculum has to expand to accommodate emerging areas. Therefore, obviously, we have to make space for the newcomers. So the old has to go. So this is an argument often used to trim electromagnetics. And obviously, we feel insulted as EM educators because this is a subject that we feel close to heart, and we, to the extent possible, we fight to protect and preserve our cherished course. So this is one challenge. Another equally, what is the one challenge? That is the expanding technological landscape, which puts pressure on curriculum and therefore on traditional core subjects like electromagnetics. That is one thing. Another thing is students changing learning styles. This is also an equally powerful aspect that appears to be impacting educational scenario on the whole, but especially electromagnetics, which is our topic for today. So these are the broad challenges. So we will just discuss as to how we can contemplate on this. Of course, I do not have any ready-made solutions to offer, but the topic needs contemplation. So some ideas we will just share on this. So how do we respond to this curricular evolution? So as we just mentioned, the expansion of knowledge impacts curriculum. That is a fact. So when a lot of new things keep coming, and we want our students to be reasonably updated about the latest technological trends, which is an important attribute a graduating engineer should have. So that is definitely putting a pressure on the curriculum. And there, of course, but can we do that at the cost of foundational knowledge? Obviously, no, because foundational knowledge is very, very important. But so also is important bringing students close to the state of art. So this becomes a competing requirement. So, of course, preservation is important because, culture is something that we want to preserve. So, similarly, electromagnetics is something that we want to, electromagnetic scholarship so rich, we want to preserve. But at the same time, we also need to accommodate newer avenues. So then on other dimensions, like students going for higher studies, doing masters, obviously they would benefit by doing electromagnetics at with a reasonable mathematical rigor. Whereas students opting for industry positions, though they do need strong foundations, may not need the kind of rigorous mathematical treatment because, software simulation tools have again revolutionized the way designs are done. So again, this way, when we have to know, one of our objectives is to prepare students for industry positions, some of them, or some for higher studies. So this presents competing demands. Obviously, this calls for more efficient coverage of course material, which is a challenge. So we have to come up with a suitable framework. We need to accommodate the fact that newer avenues are important. Our students need to be exposed to them. At the same time, we have to contemplate about the importance of foundational subjects such as electromagnetics and see the best way out of this conundrum. And some possibility, I mean, couple of suggestions is if we can integrate usually in the first 2 years, we have mathematics course, physics course, and then electromagnetics is often taught as a course in the second year. So if we can have better coordination amongst the faculties, teaching these subjects, probably we can find a more efficient space for covering all properly. And another thing is, if gaps are perceived, the first year PG courses, especially when I'm sure Cochin University has microwave engineering masters. So wherever we have, or even for communication systems, we can have bridge courses so that UG students that have come without much preparation in electromagnetics can be some intermediate level electromagnetics. So these are two, generic things. But the thing is, so we have to appreciate that when new things come, there is an inevitable pressure on current curriculum, some of which may have to be sort of trimmed or pruned. So how best we do without really seriously affecting the beauty and the richness of electromagnetics. This is something that we have to continuously contemplate upon. Then another, as I said, another important challenge is students' learning style. Here, especially those of the faculty in my age group, like I'm 50s, in my 50s, those in 40s, 50s, and maybe 60s, we reminisce about our old times and, how sincere we used to be like that. But then modern times are very, very challenging. And I think it is very, very important to appreciate so that we can try to contemplate on how to respond to these challenges. Otherwise, we flare up, we get annoyed. So students are having difficult time because too many distractions, the kind of distractions we some 20 years or 25 years back did not have. And also, this is becoming a fast food society, instant coffee, noodles kind of thing. So students also possibly impatient and may expect quick understanding, which is obviously, as we know, it is hard in a subject like electromagnetics. And then attention span, a lot of literature on how the attention span of students has been shrinking. From what I read, maybe some 2-3 years back, it was 20 minutes. I think it has further been reduced to 10 or something like that. But this is a fact because the young people are exposed to too many things. Technology helps, but there is also distraction that comes along with it. So I think, friends, it is very important to accept that teaching is challenging in the modern times. Not only teaching, also learning, because being a student in these times is also challenging. Why it is important, of course, many of us already know this, but why it is important to acknowledge this is simply because then only we can handle this with a little more balance, right? Otherwise, we get frustrated. What is this? Why are they like this? So we have to accept that modern times are hard. And obviously we are teachers, so we have to be role models to our students. So the responsibility falls on us more than on the young people. So this is important. So what are the recommendations? Some recommendations or suggestions. So please consider these as you find them appropriate. One is, I think, in my opinion, the teacher enthusiasm. That is the most important. I don't think it is about techniques or it is about technology, animation, simulation and all. In my opinion, it is primarily the teacher enthusiasm and energy that can influence students' interest in a subject. So when the teacher enters into the classroom, is it possible to, to be a center of energy and enthusiasm? That can, I believe, can make some difference even when the subject is considered hard. Then, of course, electromagnetics is conceptually rich, historically rich. There are always stories that we can, at least briefly, of course, we are all pressed hard for time. But even within all these limitations, it's possible to introduce stories about Faraday, Maxwell, Ampere. So many things of simply there's a rich repository of many historical anecdotes that we can use in the class. And then, of course, experimental demonstrations, animations can definitely help, as we ourselves are going to just see in the subsequent presentation. And please look at this. I'm not actually showing this link. You can go to this ocw.mit.edu courses, a lot of experimental demonstrations. This is from spring 2007 link, very, very useful. It lists a lot of experimental demonstrations that can be used in the class. In this context, I may mention about the IEEE APS offering educational initiatives proposals are welcome around the year. So faculty, young faculty who are enthusiastic, they can just possibly propose something like experimental demonstration for classroom use. I think that can be a good topic for proposals like this. And another very good method can be introducing student presentations and posters. In fact, one of our friends, Uday Kankoji in IIT Madras, last year, 2019, he tried this poster session where students were given topics, and then groups of students were asked to prepare posters, and then there was a poster display, faculty going around and asking questions. Obviously, there has to be a credit to this. Okay, some 5%, 10% credit, and then the way students will get involved in activities such as this, when they are provided with space for independent learning, that can really be unmatched. So I would encourage all my colleagues, young colleagues, to try these presentations and posters on topics. Some of topics that I will myself mention, but then obviously there are many possibilities. And please do visit Uday Kankoji's course web page. There some of the topics are mentioned, so all the details are there, so you can just look at that. And of course, some dependence on online video-based learning materials. Of course, I'm not talking about the kind of virtual learning that is taking place now because we have no other choice, but the chunks of videos. I mean, for brief, for example, if I have doubt about some dielectric polarization, so if short videos are there, and I am sure, or even long videos, there you can always pick the parts where your doubt, I mean, that concept you have doubt on is clarified. So a brief video sessions can be very useful as well. So these are all some of the ways we can try to keep the class interested in what we do. But the first thing, as I said, teacher enthusiasm. But how do we, again, we have discussed a lot of pressures, and with all this, how do we ensure teacher enthusiasm? That is definitely a very, very important topic, but not for this forum, for a different forum, hopefully. So that is the initial some ideas on what are the challenges electromagnetic education is facing, and how can we contemplate, how can we reflect on them so that we can possibly sort of get around or improve the current state of things. Now we will just move on to the next part of my talk, which is just sharing some ideas on an assorted topics. I will take a lot of topics and then share some thoughts on how these can possibly be taught. Again, these are just suggestions, not that these are the best ways, definitely not. Maybe you will find it interesting. Perhaps some of you are already doing much better than this, but just some ideas to share here. I think, my friends, one of the difficulties that students probably have in electromagnetics is the inability to make sense out of the maze of equations. There are too many equations. But I believe if we can just give the broad picture of electromagnetics and then keep emphasizing this from time to time, and it may be possible to place most of the equations under within this broad picture, then possibly it will make a little better sense. So what I mean by broad picture is this. So in electromagnetic analysis, or antennas or microwaves and all this, so our problem largely can be understood within this broad picture. We start from sources are current charge density and current density J. So we start from sources. They are the cause of what we want to determine, which are fields, electric and magnetic fields. So we start from sources, we estimate fields. And once we have fields, then we can estimate the parameters of interest. For example, power density, directivity, specific absorption rate, all this. In this, while fields can be determined directly from sources, but in many cases, we find it more convenient to do this through auxiliary potentials, magnetic vector potential A and electric vector potential F. So these auxiliary potentials or secondary potentials or methods that are again used as intermediate steps so that we can determine the fields more easily. That is what we do in many of the antenna analysis. So this is now, once we understand this, what we need is equations relating fields to sources, right? Sometimes via potential. So when we derive, for example, the Helmholtz equation for vector potential or Helmholtz propagation equation and all, if students understand why do we do, if we simply write, a long derivation, that itself can be boring, but then when they can't really make out as to what is the purpose of that, it can get obviously more challenging, right? So this is what we need: equations that relate fields to sources, sometimes through potentials, and then connecting the parameters of interest to the fields. This is what I think broadly we do in electromagnetics. Most of the things, the equation like Coulomb's law, so that comes under field equation, right? Coulomb's law, Laplace equation, Poisson's equation. So most of these equations can be, if they can be placed within this broad picture, that can probably make a difference. So this is the first idea for your reflection. Then, as I told, see, I'll be jumping from one topic to the other. The idea is to, some of the things that I have found to be particularly interesting, I have just picked and then I'm using for this talk. So, this perfect electric conductor. So we say that the tangential electric field is 0, right? So if we can just give some ideas why we say so. So this is a tangential electric field at the interface of dielectric to PEC 0. So how can we understand? Why do we say that? So let us consider PEC. This is actually from antennatheory.com. We can draw simple figures. We can always draw ourselves. So this is PEC, and electric field is directed like this. Now I can, decompose this electric field into two components. One is normal and another is tangential or parallel. Now, if there has to be a tangential electric field directed like this, that means I should have a charge distribution, either a plus here or a minus here, so that there can be, okay, we are talking about just above the surface of the PEC. So if I have to have a tangential field, then I should have a charge configuration like this, right? So this is PEC, perfect conductor, therefore no resistance. So charges are free to move. So when an electric field is established like this, obviously the charges within the conductor will move like this, because this is positive, therefore negative charges flow like this, positive. So these two fields will cancel each other, resulting in a tangential electric field of 0. This is a physical idea that can be used. But then how we can connect these fundamental ideas to advanced situations, that also, if you're able to do while teaching electromagnetics, then some of the students at least will find this possibly more interesting. So this implication, so when the tangential field is 0, so that means the phase of the reflected wave has to be reversed. So this is the wave that is going to be incident. So this is the reflected wave. So the reflected wave is reversed in phase so that I have a tangential electric field of 0, right? So, but then this has an interesting implication. So when I place a good conductor very close to the antenna, right, as a ground plane, then I should expect destructive interference because of this phase reversal. Because this conductor offers 180-degree phase shift, because it reverses the phase, because tangential electric field is 0. Why it is 0? Because of that, whatever we just discussed. So when the conductor is placed very close to the antenna, then we would expect destructive interference, which is often like gain enhancement. We don't want this. So, which means we have to necessarily place the antenna, the ground plane at lambda by 4, so that, so this will cause 90 degrees, so 2 lambda by 4s. Therefore, so this ensures that the waves are in waves constructively interfere here. Right. So, but then obviously this is going to present when we are interested in miniaturizing antenna, this lambda by 4 distance can be huge, right? So what is the alternative? That is, of course, yeah, before I go to the next one, an implication of this is the surface impedance of a PEC is 0, because very often now we might be using statements like the surface impedance of a conductor is low, like that. So obviously students will not know. So if you can connect it to the boundary condition, why that boundary condition occurs the way it is, and then what does it mean to a reflected wave and all that. So the surface impedance of a PEC is 0, because if you just consider this situation, a propagation vector is directed like this, a wave is incident here. So defining surface impedance as Ez by Hy, because E by H is the impedance that we define. So, sorry, Ez is 0. Therefore, surface impedance is 0 for this case. But then we don't have perfect conductors in practice. Real conductors will have some resistivity. So, which means this surface impedance is low rather than 0. So here the artificial magnetic, so-called artificial magnetic conductors, which we know as the periodic structures, they are complement to PEC, which means tangential magnetic field. It is that field which is at 0 at the surface. So which means, like, if you just look back at that equation, these becomes high impedance surfaces, right? So which means this reflects the electric field without phase reversal, which in turn means I can place an AMC very close to the antenna without, so I can miniaturize this way, right? So I can place an AMC close to the antenna, but still aid the radiation from the antenna. So we have connected boundary conditions, very basic idea, to phase reversal, to the complement to artificial magnetic conductor. And then coming to Faraday's law, these can be the electric guitar. So sometimes so music, let that be music, okay? There can be music in the class. So this is a very interesting topic that students will find. So we can ask them to give a presentation or magnetic levitation trains. So for a poster topic, these are good examples. There are many, many other examples, far better examples also, of course. So when the students are asked to study about magnetic levitation trains and then how it is related to Maxwell's equations and prepare a poster or a presentation, that will really help tremendously. So I think we should all try this. Then, of course, one of the topics very close to my heart for many years is the Maxwell's displacement current. So I think this, anyway, I will tell about a book that is upcoming book towards the end. So one of the chapters will be on displacement current, which has been thoroughly revised. Earlier, 2009, Antennas and Propagation magazine, I wrote a paper on how displacement current, the development of the concept in context can help students with a lot of pedagogical benefits. And also that chapter, that paper has been thoroughly revised and updated for inclusion in the book. So I think, a lot of benefits are likely to accrue when we consider, but this I think will, get clearer. At least my thinking on this will become clearer as we just get towards the end of this presentation. And the feedback, of course, I have tried at conferences and classrooms also. Largely, I think students have found. But again, is there a universal approach to teaching that will ensure that the entire class finds it appealing and interesting? Definitely not. Okay. So it's all, there will always be some students who find some approach interesting, some not. So that is the complexity of that we have to face. But then we have to see how, okay, instead of 10 students being interested, can I try to make it 15? Can I make it 20, 30, like that? Life is always, looking positive and then seeing how we can do this better and all that. So there is a presentation material in Fermat. So if you just search for a story of Maxwell's displacement current Selvan, so there is a presentation in Fermat which can be used in your class, or even for student presentation. We can ask the students to read this, or there are many other papers as well. Read and then just share your ideas on what you learned. So these kind of activities, so activity-based learning. So when students are given independent tasks like this, and then we should, of course, say there is nothing right or wrong. That is very important. We can't penalize. These have to be promotional and developmental activities. So students will are very likely to take these approaches far more positively. Then the next topic is antenna directivity. Okay, so like if I were a student and the teacher says that antenna directivity is ratio of the radiation intensity U in a given direction to that of an isotropic source, I will tell you that I cannot understand this. So illustrations can make this much better. Actually, I'm not a very tech savvy person. I take very long time to draw illustrations and all, but I of course do for some ideas. So instead of simply making this definition in the class, if we start with this, for example, this is an isotropic source which radiates a power PR. And of course, we would have already said that an isotropic source radiates equally. So the radiation intensity is uniformly distributed as in a spherical fashion. Now, when I replace this isotropic source by the directional antenna is more directional. Therefore, the radiation is something like this. Could be, okay. So which means the radiation intensity becomes a function of theta and phi. Therefore, it takes this form. Now, let me just consider any arbitrary direction and okay. And now define the radiation intensity of the directional antenna, ratio of the radiation intensity to the radiation intensity of the isotropic source. So that is a directivity in this direction, because directivity is actually a directional parameter, right? So this is directivity. And of course, usually by directivity, we refer to the maximum directivity. So if I just draw, so this is, let us say, this is the radiation maximum of the antenna. It is in this direction. So directivity maximum here. So maximum directivity, which is usually called the directivity of an antenna, is maximum radiation intensity of the directional antenna divided by. So when we start from here and then give the definition, then it will make far more sense. That's what I think. So please try. This is an example like that one can do for many other topics. And polarization. I mean, polarization also. See, the thing is, teachers, especially experienced teachers, 40, 50 and all, we might think that, no, what is the difficulty like that? But from young persons, 19, 20, 21, from that age, I think if we start looking from their side, then I think that can help us trying better deliveries in the class. So, so E is a vector. How I try for PG classes, I try this way. So for antenna or for UG, I mean, whenever I take. So E is a vector. So is H. So they have a simple relation, which is they are mutually perpendicular to each other and then perpendicular to the direction of propagation. So if E is like this in the far field and H is like this, or if E is like this, H is like this, of course, we have assumed that the direction of propagation is into the page here, that cross. So the direction of propagation is into the page, that is right hand rule. So they have a simple relation. Now, I can, in general, write, okay, before this, let us go to this. So if an electric field is directed like this, I can decompose this into two components. So a general electric field, which is directed like this in a rectangular coordinate system, I can decompose this into two components, Ex and Ey. Therefore, in general, I can write E here. Of course, I have used phasor representation. In phasor form, I can write an X component and Y component, and propagation is along Z direction. Okay, right, fine. So now we say the wave is linearly polarized in the x direction when x component is exists and y component is 0, and vice versa, or in 45 degree direction for when the both components are of same magnitude. Okay, like this. Now again, with reference to this picture, so E has two components, like this, like this. Now it is possible for these components to have a phase difference between themselves, right? Because they have two components, I can always introduce a phase difference between them. Then when I do that, again, in the particular instance of the components having equal magnitude and 90-degree phase shift, this is a very nice circular polarization and linear polarization. This is a YouTube video, so please watch this, and then of course you can try using in this class. So there are two components, EY and EZ, of course, in this case. So this is a linear polarization because the two components are in phase, red and blue lights.
So we are not able to see the YouTube video.
You are not able to see. So I'm sorry about it. So how do we do that? I mean, I can see that on my screen. Share. Okay, share. But share. Okay, then in that case, I think right now, I mean, maybe the audience can see themselves, or
I can see.
Oh, you can see.
Some can see, I think.
Oh, that's nice. Okay, so some cannot see.
I am seeing from Trichy.
From Trichy, so Professor Raghavan. Oh, okay, hello, Professor Raghavan. Yeah, fine. So I think we will assume in the. Sorry?
It is not visible here.
Oh,
Hello,
it's
sir.
not.
You can share your entire screen. You can share the screen again. So when you select, just select the entire screen.
Let me just try that.
Okay, sir.
Yeah, that is better.
Oh, okay. So share screen. Your screen sharing. So I go to your screen sharing.
Yeah, and in that option, you will have to check. You will have to check the option saying share computer screen. It's in the bottom of the share window.
Share screen.
Yeah.
In the share screen window, there will be a checkbox.
Yes.
Share computer sound. So you will have to check that. Yes.
Oh, okay, fine.
Okay, and then you share the entire screen. So we'll be able to see everything.
Okay.
Okay,
now hopefully, but I think I will close this and then
blue vectors,
YouTube next topic has started. Okay. Oh my God. Hello.
Yes, sir. You
meeting. Now I'll just try.
Make it full screen.
Make it full screen.
You can take the presentation, sir. The PPT.
PPT I should take.
Yes.
Okay.
And you can click the link.
Now, okay, fine. Yeah. Is the presentation visible now?
Yes.
Yeah.
Now YouTube is coming.
Now coming. Very good. Thank you very much for that. Now,
You're welcome,
please.
Sir.
Yeah.
Sir, the sound is not audible.
Sound.
Is there a sound for this video?
No, I don't think. I am not mute. No, I don't think. There's no sound for this. It's not necessary because just I think, of course, one should be careful enough in view this. So here we have E and the two components of electric field vector are same or in the same phase. Now then see it is shifted in phase. One of the components is shifted in phase. Now that becomes the locus of this resultant field, forms a circle. Is it reasonably clear?
Yeah.
Fine. So of course, the students may need a couple of views themselves, which can also always be encouraged, and that will be necessary. In fact, I am also very slow in understanding, especially visuals, not very comfortable. So of course, we can say that when the magnitudes are different, or when the phase shift is something other than 90 degree, then the resultant vector is going to trace an ellipse rather than a circle. So yeah, that's it. Yeah, fine. We can just. Is it? Shall we move on? Hello.
Yeah.
Yes, sir. Yes, sir.
So okay. So now, after showing this, we can just get to the simple mathematics part. So if we consider two E components with 90 degree phase shift, for example, so here I'm just going back to the time domain, which I just do just by multiply E power j omega t and take the real part. So the j. So there are two components of E as we just discussed earlier, ax plus jay. So we have introduced a phase shift of j to the y component, right? So when we do this, in fact, I think students can do a very simple MATLAB code to be able to see this themselves. That's also a possibility. It can be an assignment, interesting assignment. So like this, and instead of plus j ay, if I go for minus a, so leading and lagging, I can get either left hand or right hand circular polarization. But again, this the hand is, sense is always with reference to, like when we talk in terms of antenna, we have to say whether the sense is, we are referring to the sense with reference to the transmitting antenna or receiving antenna, is it not? So that, so polarization can be taught this way. I mean, this is one way in which people can consider. And related, especially a topic I really enjoy, and with dielectric polarization. Though this is a fundamental electromagnetics, this can have very significant implication when students do their project of like printed antennas, because printed antennas are all about not only the conducting parts, but also about the substrate. So a reasonably good understanding of the substrate properties can really help our PhD students or master students to appreciate when they are trying to measure, I mean, compare simulation and measurement and all. I think this is a very important topic. So how I try to teach polarization is dielectric polarization. So we consider the Rutherford model of an atom. An atom comprises a positively charged nucleus and an electron cloud. So the centers of the nucleus and the electron cloud coincides when the atom is unexcited. There is no external electric field. Now, when I when I just introduce an external electric field, obviously there is a shifting of the charges, because the electric field is directed like this, so it tends to push the positive charge up and then pull down the cloud of negative charges down. So this is external electric field. Now, this is like a stretched spring, right? So when it is stretched, it has energy, because it is stretched like a spring. When we stretch a spring, it has energy, which we can see when we release the spring, then it just comes and hits and it pains, right? So a stretched spring, an atom which is exposed to an external electric field is like a stretched spring. It stores energy, right, at microscopic level. So we can just, this is a very interesting animation again. Okay, since I have already shared, hopefully, I think this will be visible. So another 10 minutes, I will just, wind up. But this animation, cannot, okay, this is unfortunate. Why it says it cannot download? Let me see, because this is a very interesting animation. Where is that? Sorry about this interruption. Hello?
Yes, sir. Yes, sir.
Yeah.
Okay, it is all right.
Yeah, I will just try this. And since I have shared. Sorry, this is experiencing. Okay, fine. I think I'm just skipping that because it's not. But please take a note of this website. Very, very interesting animation. So what is the website? Photonicswiki.org. Photonicswiki.org. And this is polarization and polarizability. That is a specific page name. So this is a very, very interesting animation, I believe. So it shows what happens when an atom is exposed to an external electric field. So what happens? So the polarization. So we have just considered polarization. When the field is changing, alternating, obviously the polarization also is going to alternate, right? So plus becomes negative, minus becomes negative, like that oscillation, and that is very important, as we will just discuss in the next slide. So that is at the microscopic level. So when we get to macroscopic level, so obviously in the when excited by an external electric field, there is an accumulation of a net positive charge on the top surface and net accumulation of negative charge on the bottom surface, which results in an internal electric field. Okay, so this field will not be restricted only to the inside of the dielectric. Like fringe fields, there will also be fields. So when we place a dielectric in space, the presence of the dielectric alters the field not only within the dielectric, but also outside the dielectric. So I think like capacitor fringe fields, we can just understand this. So the electric field, the original electric field, is impacted by the presence of a dielectric. To account for this, we introduce electric flux density vector D. So like that. And a very important thing. Now we have said that when the electric field is alternating, the polarization also alternates. Now, this polarization, see, electric field is an electrical process, whereas the polarization alternating is a mechanical process, because atoms or the molecules or the the electron, the charged particles realigning is a mechanical process. It's often the friction can cause one of the causes for the loss factor that we discussed can be, apart from the free charges present. So this is one thing. Now, therefore, we would expect the dielectric constant to be a function of the frequency of the exciting wave. This is a very, very important aspect, especially when we deal with wideband printed antennas, or even signal integrity, as we will be briefly telling in the next few slides. So let us see whether this animation appears. Animations.physics.University of New South Wales. Yeah. Yes. I hope. So the simple harmonic motion. Actually, this is what so please look at this. Are you able to see this animation?
Yes, sir. Yes, sir.
Yeah. Okay. So this is a simple harmonic motion. So when the exciting field alternates, the polarization also alternates. So which results in a simple harmonic motion like this. So starting from this model, equations can be derived. In fact, they have been derived for the frequency dependence of dielectric constant, which is similarly loss factor. The real and imaginary parts of dielectric constant or frequency dependent. So when we use FR4 kind of material and design an ultra wideband antenna, very often we will be surprised to find our simulation and measurement results may not match. So one reason could be, not that this will necessarily be the reason. So this frequency dependence is an important aspect that can help us sort of when we try to compare measurements and simulation. Anyway, this is an important understanding by itself. So in signal integrity considerations, that becomes important. And then coming quickly to measurement. See, antenna measurement is a very, very interesting topic. I'm not sure whether we give enough emphasis while we teach, but it's very, very interesting, of course, and fascinating. With some illustrations, we can make the picture. And this is, by the way, when I was in Samir, this is a bi-rail track I established on the top of the rooftop. And I really enjoyed doing lots of measurements at the time. So by rail track. So two things, there are many things, of course, in antenna. So I will just take proximity effect and multipath interference. So what is proximity effect? What is multipath interference? Very quickly, we will just look at this. So proximity effect, as we know, like though we say far field criterion is 2d square by lambda, but that is not, that assumes a certain phase error as being accepted. But it is only at infinite distance that real far field occurs, and obviously there is nothing like infinite, we can't physically see. So any measurement facility is necessarily finite, and all our measurements are necessarily held in near fields. Of course, how near, that is how planar my field becomes in the region of interest, that of course matters. So proximity effect is related to that. And multipath interference, what is multipath interference? Let us consider, let us say the one on the left is transmitting antenna and the one on the right is test antenna. So usually our assumption or our desire would be that the transmitting antenna just beautifully just illuminates the test antenna, nothing else. But obviously, in practice that will not happen. There will be, at the minimum, there will be a ground wave. So it is incident on the ground, reflected, interferes. And obviously, we often don't do this in the free space, but inside some closed spaces like this. Therefore, the wave will also go there, and side walls, everywhere it will hit. So when we line absorbers everywhere, then what happens is the incident field is attenuated by this or absorbed by this. So resulting in the essentially a direct illumination being experienced by the antenna under test. So this is multipath interference, and we say particularly care has to be taken for low profile antennas like a patch antenna. Patch antenna measurement, radiation pattern measurement is very, very hard, is it not? Because it's low profile, therefore it often has broad beam. So a broad beam illuminates every space in the environment. So that becomes more challenging. Low profile antennas are more challenging. And antenna alignment also, I think, this is so normally it is we are able to do electrical alignment. In Samir, when I was there, we often would ensure the alignment just by visual inspection. Look behind, very interesting days those were. So look behind the transmitting antenna, see that. Of course, this is possible for horn antennas, for other aperture antennas in general. For other antennas, this could be tricky, of course. So you look from behind and then see. So what we're trying to do is mechanical, and then with a positioner, you can find out the electrical alignment also. But then ensuring real mechanical alignment is very, very tricky job for reasons that I'm not telling now because of want of time. So I will just move on. Squint is related to that. So I think this is the last technical that. Hello. Anyone? Any comments? Yeah, fine. So in high-speed digital design, so this is how we can expand the scope of electromagnetics. Signal integrity, especially with the 5G and all that, signal integrity is becoming especially important issue. And the electromagnetics is absolutely, fundamental to an understanding of signal integrity and contemplating issues for, circumventing them. So a quick understanding, and we know, and we say that a square pulse contains an infinite number of frequencies. There is a very interesting animation. So in fact, like if you see a single sinusoid also is a very rough approximation of a square wave, as we can see on the left. So when I increase the number of terms, I get closer. So when I increase even closer, I think I will skip this animation, but please see this animation. You will anyway, it is an extension of this because we don't have much time. See, Randall. This is a YouTube. I think this is no. It is UC Davis. Okay. So randall.physics.ucdavis.edu Fourier transform. So please look at that website. You can. It's a nice animation how infinite number of sinusoids can reconstruct a square pulse. So in computer science or in high-speed digital design, we I'm sorry friends, the animation link is not that, this is the one below, youtube.com watch. Okay, Anyway, search for this. Okay, so this is, I'm sorry about it. So this is the link from which I took these figures, and the one below is the YouTube link. I think we'll just move on. So the thing is, when we say, rather than simply saying that infinite number of sinusoids using Fourier series, the Fourier transform and all, an illustration, a visual illustration can definitely have impact. So we know that a perfect square wave is impossible. You know, we can't have simultaneous 0 and 1. No physical system can be simultaneously in two different states. Therefore, the closest approximation to the to realistic pulses is a trapezoidal pulse, where the there is a rise time and a fall time like this. Okay, so now a square pulse has infinite frequencies. Only an infinite number of sinusoidal signals can reconstruct a square. So by extension of this, I can understand that the faster the rise time of a signal, the larger is the bandwidth of the signal, is not? So the maximum frequency component is determined by the rise time. Because when the rise time is instantaneous, that's a square pulse, I have infinite number of sinusoidal signals. So obviously that is not possible. So the faster the rise time, the larger or the more is the frequency content in a signal. Which means we have already mentioned about the frequency dependence of dielectric. So when we deal with fast signal, fast pulses, we are dealing with more complex scenario of the frequency dependence of actually conductors as well as dielectrics. Obviously, that is going to have interesting implication that has in signal integrity. So a square pulse has infinite bandwidth. Obviously, as you just have the faster the rise time, the larger is the bandwidth. So the more is the challenge for design. So what are the challenges? Skin depth is frequency dependent. Skin depth is related to attenuation. Therefore, conductor attenuation is dependent on frequency. And substrates delay becomes dependent on the frequencies, because we know this. So dispersion is related to this idea. And crosstalk. Why crosstalk? Because high frequencies. Because I may say that this is a 5 megahertz clock, but it's not just 5 megahertz clock. It may have a 20 gigahertz signal also, sinusoidal signal also, right? So crosstalk. So high frequency radiation becomes important there. So this is a very interesting picture. You see this, let us say I transmit a nice rectangular pulse like this. Because of all this attenuation becoming frequency dependent, caused by limited bandwidth, delayed distortion, plus line noise, all that can result in a resultant received signal of this. I'm transmitting this. It is possible that I will get this because of all these factors that we have considered. So what complicates this is the frequency dependence of the dielectric and conductor properties. So which is a very, very important consideration in electromagnetics. So now to the final part of my presentation. So these are more personal, and some of you may be able to sort of see eye to eye with this. So why do we teach? So one thing is, why do we teach electromagnetics or any subject? So what are the university's objectives? What does a university aim to, right? So discipline specific skills. If I want my like electromagnetics or signal processing or any of the modern topics, so these have very short life. Shelf life is short, because the students will have a career spanning say 30-40 years. So more than my specific skills that I impart in my students, the larger objectives of education, they are important, and none of us can really forget that, because always that is the underlying theme of universities education. So obviously our graduates, we would like to see our graduates do well in life for decades together, not for 1 or 2 years, right? So necessary characteristics. So what are those characteristics? Right? Lot of characteristics apart from understanding whatever we have been discussing. So according to this, a very, very nice, link, the Chicago Handbook for Teachers, according to that, a reward of good teaching. So what is good teaching? The knowledge that we have instilled modes of thinking, how to think, okay, modes of thinking, created intellectual passion, So have we made our students curious? Have we made our students passionate and promoted forms of tolerance and understanding? In fact, Ajay Poddar's presentation sometime back about peace and harmony and all, no, very interesting. So that is the ultimate objective of education. So electromagnetics has rich content that can actually help us discuss these aspects: openness, lifelong learning. Maxwell, for example, was active for 25 years. Perseverance, right? 25 years he was focused on electromagnetics and so on. As I said, EM theory is a wonderful avenue which can help us discuss aspects such as this. And this is another important thing. So when we say that students are not showing interest, we often say because of employment opportunities in our country. Of course, for microwave engineers now it is becoming better. That's what a friend from Intel said some time back. Do students always link subjects with employment relevance? So when the teacher goes, if the teacher is able to get the students energized, if the student is able to get the students enthused about the subject to whatever extent possible, is it that they will always be linking the subject with the employment relevance? Maybe, may not be. I think may not be, but we have to just contemplate on that. So therefore, an applications only based teaching may not be very relevant, because especially in our country as of now, all electrical engineering graduates do not get employed in core industries. Okay, so many of them go to IT industries or management and many others. So why can I make EM relevant to also students who take disciplines other than like core industry? Can we think about this? This is a very interesting question for us to reflect. So therefore, a more holistic approach, which accommodates, which takes into account the broader educational objectives. Actually, as a teacher, this is how I, within my limits, I try to do. So how do we promote electromagnetic education? Faculty development. So this is what, of course, the APS Madras chapter, or many other chapters, Kerala, many chapters in India. So if we can produce 100 good faculty, they keep producing hundreds of good students year after year. Therefore, I think faculty development in the subject as well as overall professional development has to be, they are tied to each other. That is very important. And obviously professional societies can play a role. Of course, IEEE APS is a glaring example of that. And experience from IEEE APS Madras chapters, many of colleagues know, and many other chapters also. So, and another thing is expanding the scope of electromagnetics. For example, I told about signal integrity. That can be a nice subject for computer science students. And then bioelectromagnetics, that is actually, I wanted to learn this subject. So this year, what we are doing, myself and a colleague, Dr. Esther Florence, we are offering a 1-credit course to all branches of students on elements of bioelectromagnetics. So already good registration, some 30 students have registered from across branches. So that is one thing. And then summary. So importance of adapting to changes. So I appeal to my colleagues to realize, to appreciate that yes, student populations are changing, they have pressures. So we have to adapt to our models and to student learning styles. And we shared some practical ideas, and faculty enthusiasm is one of the most important things. And obviously continuous learning on the part of the teacher, and continuing to improve our teaching material, they are important. So some quick reference to additional resources. As I said, a book by myself and Carl Warnick, Teaching Electromagnetics, Innovative Approaches and Pedagogical Strategies, that is upcoming. So all the material have been submitted to the CRC press, that will be published by early next year. So, and then the IEEE APS International Symposium in Singapore next year will have a special session on EM education. So submissions are welcome. So please do submit your papers related to EM education, and then mention that you are submitting to this special session. And then 2 papers that you may find interesting is Warnick and myself, we wrote a paper, Teaching and Learning Electromagnetics in 2020. Actually, the title of this talk comes from there, that appeared in this year, April issue of the IEEE magazine, APS magazine. And another paper that you may, it is coming in the February 2021 issue of APS magazine, Lessons from IEEE APS Madras chapter on electromagnetic education in India. So please look for, and the early access might be available sometime this week. So with that, I conclude my talk. Thank you for the attention. Hello?
Hello.
Ah,
There are few questions
yeah, sure.
from Professor Raghavan.
Yeah, please.
So
Yeah.
I will share my
Ah.
screen so that you can see the questions. Can
Okay. I will just try to see how to do that. I will just come there. Stop. Okay. Now stop share. Okay. Now I have stopped sharing. Yeah.
Chat as well. In your chat.
I think I shared my screen. Is it?
Okay. You are starting to share.
Yeah. Is it a?
Not yet. I see your desktop, I think.
I shared my.
So you could check the chat bottom and the.
Yeah, I shared, but it is not coming.
Selvan sir, if you could check the chat.
Yeah. It is better.
Chat. Okay. Chat. There was. Yeah. Okay. Important subject like radar acoustics are removed from.
Yeah.
I mean, Maxwell's equation are not required for designing microwave integrated and with transmission alone. Easy, def your comment, please. Yeah. Actually, both are. Yeah. First, coming to radar acoustics, navigational aids are removed from EC syllabus. It's a very unfortunate thing. So obviously radar is such an important part of our life, but then as I said in the beginning, that is what, see, when we face conflicting pressures in life, there are too many pushes and pulls that subject, because everyone advocates for their own subject and interest. It's a very, very complex situation. But obviously I, along with Professor Raghavan, will feel bad. Even now, actually, in Anna University, I think antenna and microwave engineering, they have been clubbed into one subject that has become an elective. It used to be a core, now it is an elective subject. So which is very unfortunate. So such things, but we try within our limits, but then others are also trying to advocate a newer subject. So that is one thing. And then Maxwell's equations for designing transmission line theory, again, yeah, definitely. I mean, this is also in fact recently I saw a book which also talks about transmission line theory based approach. Definitely, I mean, I agree. But again, Maxwell's equations, as I said, to me, I mean, as in my personal sense of Maxwell's equations, more than applications, I see the conceptual richness, the scholarship, and the intellectual beauty of that. So that is what, I mean, as I have tried to say. But this, I mean, I agree with Professor Raghavan's comment.
Any questions from the participants? So if there is no questions, let us thank Professor Selvan, a teacher with high enthusiasm in electromagnetic theory, and explained vividly the concepts of boundary condition, AMC, directivity, etc. I hope this will trigger the younger generation with more idea and animations in EM theory. The talk is very interesting, sir. Provides motivation to the younger teachers and scientists in this field.
Thank you.
Because at present, most of the teachers are transferring the knowledge without knowing the subject by simply PPT sharing. I think your lecture will motivate the younger generation. Thank you, sir.
Thank you. Thank you very much. Thank you. I wish this symposium all the best as it next few days.
Sir, we are extremely thankful to you for sharing your deep knowledge about teaching and learning electromagnetics in 2020 with us. And your session was full of enthusiasm and knowledge. Thank you, sir.
Thank you.
I also thank the distinguished chair of the session, Professor Mohanan, sir, for his valuable presence. Thank you.
Thank you. Thank you very much. Bye.
Bye.
Sir, I request all the panelists to switch on the video to take a screenshot.
Where is Selvan, sir?
Here I am there. Just now I enabled my video.
Taken?
Over. Finish?
Yes, sir. Yeah,
Yeah.
thank you.
Okay. Bye, everyone. All the best.
Thank
All
you,
the
sir.
best.
Thank you, sir.
Yeah, okay. Bye.
Bye.
Bye, Professor.